If you only truly master one thing in web hacking, make it this. HTTP is the language every website speaks, and every single attack you'll ever run is just a modified HTTP message. Change one header, one method, one cookie, and you can bypass logins, steal sessions, or break access controls. Most people treat HTTP as background noise. Hackers read it like a native language. In this episode, we go deep. Requests, responses, methods, status codes, headers, cookies, and how HTTPS wraps it all in encryption. By the end, you'll never look at a web request the same way again. Let's start from the ground up. What actually is HTTP and why is it so hackable? The answer is simpler and more powerful than you'd think. HTTP stands for Hypertext Transfer Protocol, and here's the secret that makes it a hacker's dream. It's just plain text. Every request, every response is human-readable text you can look at and edit by hand. It works on a simple loop. The client sends a request, the server sends back a response. One request, one response, then it's done. And that leads to the most important property of HTTP, it is stateless. The server remembers nothing between requests. Each one arrives with no memory of the last. So how does a site remember you're logged in? It doesn't. It makes your browser prove who it is on every single request, usually by sending a cookie. Hold that thought, because that mechanism is where a huge number of vulnerabilities come from. Text-based, request-response, stateless. 3 properties, and all 3 are things you can exploit. Let's dissect a real HTTP request line by line. It has 3 parts. Part 1 is the request line, a single line with 3 pieces, the method, the path, and the protocol version. For example, get/account HTTP 1.1. The method is the verb, what you want to do. The path is what you want it done to. Part 2 is the headers, a stack of key value pairs, 1 per line, carrying metadata. The host header names the website. The cookie header carries your session. The authorization header can carry your credentials or token. Content type tells the server what format the body is in. There can be dozens. Part 3, after a single blank line, is the body, optional, and only present on requests that send data, like a post. This is where form fields, JSON payloads, and uploaded data live. Here's what matters. Every one of these pieces is under your control. In a tool like Burp Suite, you intercept this request and rewrite any line you want before it reaches the server. The method, the path, every header, the body, all editable. The server's security depends entirely on how it handles input it cannot trust. Let's talk about methods, the verbs of HTTP. There are more than you think, and some of them open doors most developers forget are even there. Every request starts with a method, and each one is a different intention. GET means retrieve something. It should only read data, never change it. Post means submit data, create something new, like a comment or an account. Put means replace a resource entirely. PATCH means partially update one. Delete removes a resource, then the quieter ones. HEEEE. Ed is like G but returns only the headers, no body. Options asks the server which methods it even allows, and for a hacker that's reconnaissance, because it can reveal methods the developers didn't mean to expose. 2 ideas you need. First, safe methods like GET are not supposed to change anything on the server. When a GET request does change state, that's a bug and often the root of a CSRF vulnerability. Second, idempotent methods like put and delete should give the same result whether you send them once or 100 times. Why does this matter? Because developers often protect the front door method, post, and forget the same action might work over PUT or delete or with a method the docs never mention. Testing every method against every endpoint is one of the simplest, highest value habits in the game. When the server answers, its response mirrors the request, 3 parts again. Part 1 is the status line, the protocol version, and a status code with a short reason. For example, HTTP 1.1, 200, okay? That number is the headline of the whole response. Part 2 is the response headers, metadata about what's coming back. Content type tells your browser whether this is HTML, JSON, or an image. Sect cookie hands your browser a cookie to store. Location tells it where to redirect, and a family of security headers quietly control what the page is allowed to do. Part 3, after the blank line, is the body, the actual content, the HTML of the page, the JSON from an API, the bytes of a file. As a tester, you read responses for signals, an error that leaks a file path, a status code that reveals whether a user exists, a header that's missing when it should be there. The response is the server talking back, and it says more than the developers intended. Those status codes aren't random, they come in 5 families, and once you know them, a response tells you what happened before you even read it. The 1xx family is informational, rare, mostly ignore it. The 2xx family means success, 200 is okay. The classic, 2000 means something was created, 2004 means success but no content. The 3xx family means redirection, 301 is a permanent move, 302 a temporary one, and open redirects, a real vulnerability, live right here. The 4xx family means you, the client, did something wrong, 400 is a bad request, 401 means unauthenticated, you need to log in, 403 means forbidden, you're logged in but not allowed, 404 means not found, 409 means you're being rate limited. That gap between 401 and 403 is pure gold for a hacker probing access controls. And the 5xx family means the server broke, 500 is a generic crash, often triggered by unexpected input, which is exactly what you're feeding it, 502 and 53 point to gateway and availability issues. Read status codes as feedback, and the app starts telling you where its soft spots are. Now, headers. If methods are the verbs, headers are where the real control lives and where a surprising number of hacks begin. Headers are the metadata of every request and response, and dozens of them matter. On the request side, the host header tells the server which site you want, and tampering with it leads to host header injection. The user agent identifies your browser, but it's just text you can fake. The referrer says which page you came from, and apps that trust it for security are asking for trouble. The authorization header carries tokens or credentials, and the cookie header carries your session. On the response side, the server sends its own headers. Set cookie plants a cookie in your browser. Content type declares the format, and getting it wrong can itself cause vulnerabilities. Then there's a special group, security headers. Content Security Policy, or CSP, limits what scripts a page can run, a key defense against cross-site scripting. Strict Transport Security, or HSTS, forces HTTPS. X-frame options controls whether your site can be framed, the defense against clickjacking. Here's the hacker's angle. On the request side, you tamper with headers to attack. On the response side, you check which security headers are missing, because a missing header is often a vulnerability waiting to be reported. Reading headers is half of web hacking, and that brings us to cookies, the single most attacked value on the entire web. Understand cookies, and you understand sessions. Understand sessions, and you understand account takeover. Remember, HTTP is stateless, the server forgets you after every request. Cookies are the fix. Here's the flow. You log in. The server creates a session for you and sends back a set cookie header, something like session equals a long random string. Your browser stores it, then automatically attaches it to every future request to that site. That cookie is now your identity. Whoever holds it is you, which is exactly why stealing it, session hijacking, is such a price. Now, cookies have attributes that control their security, and this is critical. HTTP only means JavaScript cannot read the cookie, which blocks an attacker from stealing it with cross-site scripting. Secure means the cookie is only sent over HTTPS, never plain HTTP. And SameSite controls whether the cookie is sent on request from other sites, the main defense against cross-site request forgery. When any of these flags are missing or misconfigured, you have a finding. A session cookie without HTTP only, exposed to an XSS, is a full account takeover. This one small header is where authentication lives or dies. So far, everything we've described is readable text flying across the network. On plain HTTP, anyone in the middle on the same Wi-Fi on the network path can read all of it, your cookies, your passwords, everything. HTTPS fixes that. The S stands for secure, and it's HTTP running inside a layer of encryption called TLS, Transport Layer Security. Before any request is sent, the browser and server perform a TLS handshake, they agree on encryption keys, and the server proves its identity with a digital certificate signed by a trusted authority. From that point, everything is encrypted. A man in the middle now sees only scrambled bytes. This is why the padlock matters, and why sending sensitive data over plain HTTP is a reportable flaw. But notice something important. HTTPS protects data in transit, it does nothing about a vulnerable application. A site can be perfectly encrypted and still riddled with SQL injection and broken access control. Encryption secures the channel, not the code. Never confuse the two, so let's zoom out. Why did we just spend all this time on one protocol? Because HTTP is the attack surface. Every web vulnerability you will ever find is expressed as a modified HTTP message. Changing a method to reach a forgotten endpoint. Tampering with the header to inject or bypass. editing a cookie to become another user, feeding a malformed body to trigger an injection, reading a status code to map what exists. A tool like Burp Suite exists for exactly one reason, to sit between your browser and the server and let you intercept and rewrite these messages before they're sent. When you can read an HTTP request and instantly see every value you control, you stop being a user and started being a tester. That's the shift this whole episode was built to give you. Master the protocol, and every technique in the rest of this series becomes just a specific, clever way of editing text. Let's lock it in. 1. HTTP is text-based, request response, and stateless. 2. A request is a method, headers, and an optional body. 3. Methods are verbs, test all of them, not just the obvious one. 4. A response is a status code, headers, and a body. 5. Status codes come in 5 families, constant feedback. 6. Headers carry the control, missing security headers are findings. 7. Cookies carry a session, HttpOnly, secure, and SameSite decide if it's safe. And 8. HTTPS encrypts the channel, but never the vulnerabilities. Screenshot this. Every hack from here on is a variation of editing one of these. If this made HTTP finally click, you're now ahead of most people who call themselves hackers. Subscribe so the rest of the foundation lands in your feed, because we build straight up from here. In the next episode, we cover HTML, CSS, and JavaScript, but only the parts you actually need to find bugs, the exact things that turn into XSS and DOM attacks later. Drop a comment which header or status code surprised you most. I read them all. See you in the next one.